So, good morning and welcome to this breakfast seminar. I hope everybody has some breakfast. I at least had a cup of tea. So today, this will be the second seminar in our short series of seminars that are targeting vulnerability of modern society. And we exemplify it by large-scale cyber attack against Ukraine. And today, it will be my old friend and colleague, Dr. Alexander Adamov, that will go deep down into the WhisperGate. WhisperGate is a part of the malware that was used, the attack 13th of January. So, Alex, this screen is yours.
Thank you, Anders. Good morning, everyone. And as Anders said, today's webinar is going to be a continuation of the first webinar in the series devoted to the attack that happened on at night from 13th January to 14th and went out of operation numerous Ukrainian government websites. So the attack actually started with the face. You can see the picture that was published on many government websites in Ukraine. And this is, for example, the picture taken from the Ministry of Education and Science of Ukraine. And Anders and Alexei told during the previous webinar that how it happened about the attack vectors. And today I would like to focus on the analysis of WhisperGate components. So what WhisperGate is? Immediately after the attack, Microsoft on January 15 published the report where they stated they discovered destructive components on the computers, or I would say on the servers that were used to hosting Ukrainian government websites. And those components, they reminded me NotPetya operation, where the state-sponsored hackers, supposedly from Russia, delivered like fake ransomware, or how it was later called destroyer, through supply chain attack vector using Medoc accounting software. And the purpose of NotPetya was to destroy computers in Ukrainian organization, and even out of the border, even though it was not planned, but NotPetya escaped and even managed to affect Microsoft's IT infrastructure. So in this case, we see that WhisperGate has several components, and two of them, they are most dangerous. They can be called destroyers. The first one, or also called stage one, this is the MBR Writer. So I'm going to just switch to another publication by S2W company, where they just draw the cyber kill chain. So the first destructive component, or destroyer, which is also called stage one, overwrites the MBR. So it puts its code into the MBR. This code prints the ransom node at the boot of the system. And also another feature of this file, of this destroyer, is to damage the data on the disk, on the bootable disk. And it overwrites at numerous locations with some repetition. It writes the ransom node to the disk. Then the second component, which is destructive, is called file wiper. You can see it at the right bottom corner, wipe target files. So this one is executed, is called also stage 4, and executed at the end of the attack, and is used to scan the file system, filter out the files based on the extension, usually documents, some files that contain sensitive data, and wipes the first, almost roughly saying 1 megabyte of data at the beginning of the file with a byte CC. Just wiping the data is not possible to recover. On the contrary, ransomware encrypts data in the files and store the key, and then ask to pay a ransom in order to recover the files and provide the decryptor to decrypt the files. In this case, we see only destroyers. So they wipe the files, they replace MBR, and they destroy the data on the disk. And during this session, I'm going to talk about all the components. So as you can see, besides stage 1 and stage 4, we have a stage 2. Stage 2 is a Trojan downloader. This Trojan downloader goes to Discord and use a CDN network to download the malicious, another malicious component, which is called stage 3. And stage 3 is a Trojan-Dropper. So in the resource section I'm going to show later, it contains encoded scripts and files like a file wiper, and it is used to decode the resource data and execute, for example, file wiper. And for execution, it uses the techniques called process hollowing. Process hollowing, which means it starts legitimate process, stage 3. In this case, the attackers use install util. It's a Windows legitimate application. They copy this application to temp folder, started, and then started in suspended mode. And then they replace the content of the install util process with its own. So they just injected the file wiper. And then they resume the install util process, and user would see like a legitimate application just destroying the data on the computers. So that's a major idea, and during today's presentation I'm going to demo how it works, and just we'll take a look at the components. So let's start with stage 2. So stage 2 is a .NET application. So if we open the details, the properties of the file, and we'll find out that it contains a digital signature. It's Microsoft Windows digital signature, which is used to sign Windows components, Windows files in the operating system. But the thing is, the signature is not valid. Supposedly it was copied from another application and just attached to this file. So this supposedly done for defense evasion, because some security solutions, they, for example, can check if the file is digitally signed, but they may not check if the digital signature is valid. And it's essential to perform, because otherwise it's easy to trick the security solution. And another interesting peculiarity of this file is if we go to details, which represents the data from version infrastructure, which is usually comes in the resource section, we'll find that some of the data here are written in Russian, which is also points me to the idea that the creators of this file, they just used, for example, in this case, Explorer application, but from Russian localized Windows. And they just copy this version infrastructure to this file and use it probably not to attract attention again from the security solutions. But the fact that these details, they come from Russian version of Windows operating system may give us some thoughts about the attribution of this attack. By the way, the defaced picture that I have shown you at the very beginning of the presentation, the attackers, they artificially embedded geolocation data pointing to some institution, to some building in Poland. But the thing, it's not photography, and it doesn't make to embed any geodata into this picture. So of course it's a false flag. And this false flag was intentionally introduced by the attackers. But if we talk about this particular, case, I think that's can be used as a real attribution flag. Okay, nonetheless, it's hard to prove the connection, but from the geopolitical context, it's more or less clear. By the way, the Ukrainian authorities, they attribute this attack to the state-sponsored hackers from Belarus. But as you know, I hardly believe that the hackers from Belarus would act without the confirmation from the Russian. Okay, and what we can, if it's .NET application, and how we can recognize this as a .NET application, first we can use some scanners, static analysis scanners, for example, PID, and we can see this is a .NET, Microsoft Visual C#. We can also go, for example, to the import address table and see, okay, if we see this import mscore.e.dll, this is a sign of .NET application as well. So if it's .NET application, it means we can use dnSpy, probably the most popular tool for the compilable .NET application. And here you can see these details that we already seen in the details tab in the properties of the file. And if we roll out the structure, then we can find some modules. And as you can see, it has this so-called control flow obfuscation, which means it has this a lot of switches, a lot of branches, and the execution of each branch is decided in runtime based on some parameter, based on some variable that is changed, and based on the values of this variable, the appropriate branch is executed. In this particular case, we have, for example, num2 as a variable that is used to make a decision which particular branch to execute. Then what I would recommend is when you start analyzing any piece of malware, you can just execute it and see in a process monitor what's going to happen. And the same I propose to do in this case. So we need to set filter. I'm going to use the process name stage2.exe. And in addition, you can run a network sniffer to track any network activities, because the process monitor, even though it has like 4 types of monitors, including network activity, this only shows the request, like high-level network events initiated by the process. It doesn't show the actual packets sent and received. And that's why I'm going to use my Ethernet and start sniffing the file. So then I can start the process. As you can see, there is some traffic. It's a TLS, but we don't know exactly to which particular service it will go. So for simplicity, you can just disable registering file monitor and see if there is any network activity. So there is some delay. And finally, Finally, you can see this connection to the remote server, and this is the IP address of the remote server. And in our Wireshark, we can set up the filter using this IP address: 162, 159, 129, 233. So that's it. And here we can see this is a TLS handshake, and there is a client hello packet here. And we can see that this IP address belongs to CDN network of Discord application. So as I mentioned in the very beginning, this application is a Trojan downloader, and the main purpose of this application is to download like stage 3 component from using Discord application. Of course, at the time of analysis, this component was not available, and that is why you can, by the way, download it from one of the online sandboxes or other sources. So now we know that it connects to CDN Discord, and for example, in the compiler, you can search for CDN, something like that, and finally you can see that they have a method download data, and it downloads the file with some strange name and extension JPEG. So supposedly it's a picture, but of course it's not going to be picture. I'm going to close my Wireshark, and I'm going to just disable my monitor. So if we go to stage 3, we can see that this picture that was downloaded from one of the malware shared services. And if I open this file, for example, in hex editor, just to view the content of the file. So it starts from zeros. And if we go down, you may recognize, if you are familiar with the P structure. So this is magic bytes of the executable file MZ that actually precedes the legacy.header. This is the ms.stub written in the reverse order. And finally, you can see the name of the sections. And so here, the modern P header starts. So it's just an executable file, but with the bytes reversed. So it's easy, of course, to reverse the bytes and have a P file. So in fact, it's DLL. So we can identify this, for example, viewing the optional header. This is a DLL. It's not executable, it's DLL, even though both are P files. So stage 3 DLL is executed by stage 2. So stage 3 is the Trojan-Dropper. It contains malicious component in the resource section, and stage 2 just downloads stage 3 and then executes. And if we just to save time, we can refer to analysis of to one of the analyses provided by the researchers. There is a name of the methods here that is used to call it's called reflective loading of the DLL to execute the payload of stage 3. And yeah, this is a fill reflect item, and this is the name of the method that's going to be executed. But because the downloader cannot download stage 3 DLL from Discord, it cannot execute this method. It cannot launch stage 3. And that is why we will miss this part. But what I'm going to do is just take a look at stage 3 structure. So stage 3, if we go to PID again, it's again .NET. And by the way, both stage 2 and stage 3, they are pretty similar. They are written in C# and these are .NET applications. And by the way, if we take a hash of one of these components, in particular for, let's say, for stage 2, we can use Intezer Analyze service, which finds the similarities between the families, between the malware families. And you can find that the Trojan downloader has like almost 12% of quasar RAT, it's so-called code genes, but they can be attributed to some code pieces or functions that are similar with this remote administration tool. Similarly, if we take the hash of this DLL, of stage 3 DLL, already reversed, and then just search for this DLL, you will see that, yes, there is, by the way, there is a strong attribution to WhisperGate family. It found malicious packer, actually obfuscator, it's a commercial obfuscator used for stage 3, it's called isfuscator. And also a lot of genes, like 58, 56 for some admin tools. Synapse Software LC, Synapse X Launcher. So they just use this supposedly like freeware or open source tool and build this Trojan-Dropper based on this tool, or just use some shared components DLL inside of this inside of this malware. So this is this tells us that the attacker, they reuse some code from the internet when creating. And if we open again in DNSpy, so this is DLL. As you can see, it's substituted with the original name of the DLL that was used during the attack. And this name is written in version infrastructure. And well, those are resources that contains encoded components. And if we take a look at these resources, maybe we can find some executable code here. But instead, we can see that seems to be, it has no any magic bytes or headers. And based on this repetitive structure of elements, and so this data looks not that have not very high entropy. I would suggest that this file had been encoded using linear cipher, some linear transformation, supposedly based XOR based. And if we, for example, want to find where this in which part of the code this stage 3 DLL decodes the resource section, we can just start searching for the name of the section. Yeah, there is one thing here that complicates the analysis. It's obfuscation. You can see it's not only about control flow execution, but also the names of the variables and the names of the methods they were obfuscated. It's hard to read, it's hard to navigate. And that's why it makes sense to use the obfuscator for stage 3. As I mentioned, the attackers use commercial obfuscator. And so we can use defo.dot, probably the most popular defuscator. But the thing is, when I tried defuscating this file with defo.dot, I found that it drops some strings that are used as arguments, some valuable strings. And there is another unpacker called AIO, which is actually based on defo.dot, but for some reason it just works much better than the original one. So I can put it here, select the method. Don't ask me why this method, just. And finally, yeah, we have this defuscated. It doesn't fix the whole DLL, but it fixes the strings. And with fixed strings, it will be much easier to analyze and navigate the application. And again, we go to resources and try to find out where this resources was used. And here we can see the method move next, and it has some base64 encoded strings. And by the way, I would recommend for base64 decoding, there is a very useful tool called CyberChef. Just if you want to see the actual parameters sent to the function or store it. So this is the name of one of the DLLs. So this will be concatenated with .dll extension. And then we can see, so this somehow relates with this resource section. And after this string, we can see the call of the method 0, and it calls method 1. And if we go down, we'll see that there is method method 6 here, which contains also some base64, but that's not strings, that's an error used to decode the data. And this is a decoding procedure. As I mentioned before, it's a linear transformation. This is XOR-based decoding. Well, this is how it's connected. And actually, even though you don't have a loader for this DLL, still you can manually decode these resources and use them in the analysis. If you want to follow the dynamic analysis way, I would recommend to read the paper written by Max Kersten, supposed to be the researcher from Netherlands. And he suggests to create a simple loader for stage 3 DLL and debug it using, for example, dnspy decompiler. It has also debugging capabilities. Well, that's I'm not going to debug it, just to show you how to work with the .NET application with the decompile code, and how to search, how to defuscate if it's possible. And the next step will be debugging or decoding the malicious components stored as resources of this stage 3 DLL. To save our time, I propose later to consider this file viper.exe. And well, let's probably, as for any file, we can start with basic static analysis, and this nothing found, which means this was created in a very basic compiler. And again, if we use, let me check if I have the hash for file viper. Not here, but anyway, we can easily create the hash. sorry, that's not the hash. MD5. And then we can use this MD5 at our Tether analyze to find similarities with any other malware. And it's interesting that there are no any relations to other malware. This can be considered as like a brand new piece of malware, but it has a MinGV library compiled in. By the way, if we take a look at stage 1 and stage 4, stage 1 is MBR Writer and stage 4 is the File Wiper. They are very much similar. I would say they were created both with MinGV library, and they were created, I would say, by the same developer. Okay, let's take a look at File Wiper, and to do that, I'm going to use IDA, disassembler. So of course, you can start it using, for example, process monitor to identify the behavior, but to save time, we will pack all these activities into one session. So first I need to rename it. So it's going to be File Wiper. And I would need File Monitor enabled for this analysis. And as we know, this is a File Wiper. So it's going to write some data to files, right? And it will use some file write operation. And because it uses MinGV, like an old school library, we can go to this Microsoft runtime library. And here we can find fwrite. Yeah, you can look for write file, Windows API function, or in this case Microsoft Visual Studio runtime library is used, and so we just put breakpoint here. Next thing, if it's gonna search for files that are suitable for encryption, that have specific extensions, it should contain these WinAPI functions for finding files. By the way, any ransomware, you can detect ransomware just by detecting import address table if it contains this find next file and write file operations. So here, again, the call to find next file. Yeah, I think we are good and we can start debugging. So we stop at find next file. This is the first step of this malware. And we just click on the return address and we go back to the procedure from where this find next file function WinAPI call was executed. And so this is the place where it searched for files. And if we go down, or just want to find the comparison operation, and for this we can, for example, run until return, and one more time because it just come out of find file. Well, this is a error handler, so we don't want to see it. I just see some. I just want to find some references to to the strings that are used to compare the findings of the findings file. That's what I'm looking for. And yeah, let's run one more time until return. And to find any references to strings. Well, we see, by the way, here some comparison between two strings, but I want to find the place where there is a reference to the extension, for example, that are used to filter the files, to create the list that will be used to wipe the files. And yeah, this is some dots that I use as a delimiter. By the way, if you can't find the references to string, you can also use in the debugger strings u. Just come from another end of the question. And here it generates all this interesting strings. And yes, this is exactly what I was looking for. This is a list of extensions that I used for filtering files when searching. And yeah, this is an array, string array. And this is where it's used. This is a comparison function. And yeah, we can just try to find the reference from where it was executed. And it was executed from here. By the way, there is another check for exclusions. So as you can see, this ransomware doesn't encrypt files in recycle, not encrypt, but wipe files in recycle bin because it's pointless. Home drive and whatever this means, and the Windows folder. By the way, this strings is used to delete the original file just to hide the traces of the attack. It starts pinging some arbitrary address 5 times. And after that, after this delay, this is just introduced for delay. And then it just calls the delete, and there should be the name of the file that should be deleted. So yeah, let's go further because we have not much time. I'm going to just remove breakpoint from find next file, and now we are in the call of file write function. I'm going to again return to the function from where it was called. And that's interesting because this is actually wiping the file. So buffer, this is the data that is used to wipe the file. This is, as I mentioned, byte CC is used to wipe the data. And we can even watch this buffer in hex dump. We can go to the address stored in EDX register, and yeah, this is a huge buffer with CC that is going to be loaded, written to the file. Then the element size 1 byte and the amount of bytes here. So in many articles, I have seen that it's 1 megabyte, but in fact, it's not 1 megabyte, but just a little bit more, just 1,048,566 bytes. But they just use hex value for simplicity and just some big amount of data. And then if we I want just to return from write function. I don't need to debug system functions. Yes. And if we go to process monitor, so we might see actually if we resume the operation here and here. Sorry, process monitor. So we will see or not see. Yeah, here it was just frozen for some time. I'm going to disconnect it. And if we take a look at the files, so 1 megabyte of data has been written to the file, and then it was renamed using some random characters in extension. Here. So that's how File Wiper works, but that's not the most interesting part. Well, this is quite basic one. I'm going to next analyze stage one. Stage one is MBR Writer. To do that, because it's going to get direct access to a physical disk, it will require administrative privileges. And that's why if I want to debug and want to have this successful request to get the access to physical drive, I need to start my debugger with administrative privileges. Actually, you can easily figure this out once you have failure return code from the create file function, which requests the access to physical disk. Then I need to open stage one, and you will see that the structure of the file is pretty similar. So it's the only difference, it has this write file, probably because so I'm going to set breakpoint here. And yeah, let's set our filter for stage one. So we set breakpoint on write file, and this is probably the most interesting part in this malware, and we can start debugging. I return to the place from where it was executed. As I said, the structure of stage one and MBR Writer and stage four File Wiper is pretty similar. So let's take a look at write file function here that was executed, and the parameters that are sent to create file before to get the handle to the physical drive, and the actual write file, the buffer that is going to be written, and so on. So by the way, when you debug WinAPI malware for Windows, I recommend just using MSDN, and because it provides all this explanation for the parameters and the return codes, success or fail or errors of the execution of the function. Let's get back. But the good thing that IDA has a flirt library with signatures that identifies the WinAPI calls. As you can see, no protection applied to this file. So File Wiper and MBR Writer, they are not protected by any packer, protector, or obfuscator. So it's easy to debug and easy to study for example, for students. Okay, let's start from create file here. So the file name, as you can see, they want to get access to physical drive 0. So this is a VM, it has only one physical, let's say physical drive. And full access, they want to get full access. And if we take a look at the file monitor, you will see that they successfully get all access to my physical drive because I started my debugger with administrative privileges. Then it gets the handle and uses handle to run the write file. So number of bytes, 200 hex, or in decimal, it's going to be 512. This is the exactly size of the disk sector and size of the MBR. So MBR is stored at the very first sector of disk partition of bootable disk. And so here we have the buffer that's going to be written. That's quite interesting. Let's view it in hex again. By the way, it's already opened me at that place where I have the code and the ransom node that is going to be stored in MBR Write instead of MBR. So here there is a piece of data that doesn't look like a data or something like ransom node. It's a code that's going to print this ransom node in console. We're going to see it a little bit later. And then starting from here, they have some kind of like anchor prefix, which is 5 capital A's. I would say they were debugging this malware and they just use this anchors to easily locate the modifications of the hard disk or MBR, whatever they need. And if we go to this code and convert this into the code, of course, it's not correct because currently the application is loaded as a 32-bit application, and MBR is executed as a 16-bit application. But still, we have this first instruction, jump short +2. So in fact, what it does, it just jumps to the next instruction, which has the address +2. So this address is df00 and this df02. So so what I have question to you: what is the purpose of this jump instruction? And I started the poll in Zoom. Please provide your answer. What do you think? Why they have like the very first instruction of the MBR code that is going to be written instead of original MBR is jump short +2. And as I said, this operation just jumps to the next instruction. What is the purpose? If you already provided the answer, you can read, for example, the message that is going to be printed. Your hard drive has been corrupted. In case you want to recover all your hard drives of your organization, you should pay $10,000 via Bitcoin wallet. And there is a Bitcoin wallet that you have to use to send this money. Or Tox ID, and send message using Tox ID. And this is a message. Of course, this is not ransomware, and this is not the purpose of. There is no need to make money on that because it's just destroyer. And this IDs and these Bitcoin wallets can be used as a false flags, just to make it look like it was created by some, for example, security researcher or activist that use this Bitcoin, for example, in some donations. Okay, so I got more and more answers are coming. So I'm going to end the poll and share the results. So the majority of you, like there was no like one answer that collected more votes. There is a almost equal distribution between the first answer, change the value of instruction pointer. Well, yes, it changed the value of instruction pointer, but still, what is the purpose of changing the value of instruction pointer? Yeah, sometimes compilers, they are too smart and they try to, for example, feed the CPU pipeline, and then they try to introduce different kind of they try to optimize. There is optimization for performance or optimization for size of the application. And depending on the goal, the compiler may optimize and try to use the instruction to parallel the execution. Code obfuscation, well, yes, it can be like a control flow obfuscation, or just introducing some garbage instructions, and you can get lost in the tons of operations, assembly operations. Code data alignment, yes, it can be, but we don't know why this needed, because at the end of the message they still have some space. This is space here, and there is also space, zero space here before this data. Well, maybe I don't have like 100% sure confident answer to this, because I'm not the author of this malware, but my idea is it was used for debugging. Why? Because if you want to attach your debugger, you need to somehow synchronize the process and the debugger. So if you just let execute the code in MBR, you will just miss this code because it's very small and it will be executed just in a matter of milliseconds. And you need to somehow introduce a delay during which you can attach your debugger. So, and here I have another question. So if it writes this code into the MBR, how can we debug it? So even though you don't have experience like debugging MBR or kernel, just try to guess. I'm going to explain the variants. The first variants, I use VirtualBox built in VM debugger. So because my VM currently is running in VirtualBox, I'm going to use VirtualBox because it's a hypervisor and it controls execution of my VM to debug this MBR. Second answer, Hyper-V paravirtualization provider. It's so complex name for transport, actually for debugging transport. The idea is you can leverage the included by default Hyper-V debugger in Windows. It's available since Windows Vista, and use Hyper-V as a debug server and connect your Windows debugger, WinDebugger, to the remote host that is running on your virtual machine, or it can be somewhere in your network. And you can remotely, using WinDebugger or any other debugger, you can remotely connect to the machine using this Hyper-V service, a debugging service that will work as a debugging service, as a debugging server, providing the ability to send and receive debugging comments. LiveKD, it's a live kernel debugger, which means it's executed during the runtime. So, for example, you work on your don't do that. When you work on your, for example, computer and you want to debug your kernel, so it's still possible. You can run LiveKD and debug your operating system on your computer, which you use for your work right now, and in real time. Well, that's not the best idea, because once you change some kernel structure or kernel objects, so your operating system will crash. And I don't know if you will be able to restore it very easily. Then connect WinDebugger remotely. This is related to using Hyper-V service, back service that is available in Windows. and you can connect WinDebugger or any other debugger remotely. And yeah, so hopefully you made your decision, and the majority of you stated that using virtual box built-in VM debugger is best option in this case, and I completely agree, because in order to establish this server-client communication for remote debugging, you need to first start debugging service. And if we use, for example, Hyper-V, our virtualization provider available since Windows Vista, we need at least wait until OS loader, operating system loader starts. And once OS loader starts, it will start immediately the debugging service. But MBR is executed before the OS loader. That's the problem. And just to understand, the MBR is executed after BIOS or UEFI code, which is available in firmware on your motherboard. It starts MBR, and in your firmware, you can provide in configuration your bootable disk, or it can be auto-detected, and your firmware is going to just execute the first instruction available on your bootable disk. And this is MBR. This is the first byte of the MBR. And then after MBR, MBR starts the operating system loader. This is step number 3. Okay, that's it. And then if we are going to write this code and then, for example, reboot the computer, we will not be able to attach the debugger because we need some, we need to interrupt the program. How to interrupt the program? The best way that works with the most debuggers is just introduce infinite loop. And that's why we have this instruction at the very beginning of MBR. So we can modify this to jump to itself. In such case, we can come up with the infinite loop. And when started, our virtual machine will be waiting until we attach the debugger and jump to break this infinite loop forcefully and jump to the code which is located here below. By the way, if we go down, you will see that there is int 10 used with parameter HA0E, which is it's a mode for this interruption, and this is saved in AH. This is a typical practice. I don't know if I have this this page here. I just can Google like int 10. Yeah, even Wikipedia would be enough to understand how it works. So we have OE. This is a teletype output. Teletype output sounds really scary, but it's just printing the text to the screen, to console. And yeah, just go back here. So then the next, before we write this data to MBR, because currently it's stopped at file write call, we need to change this data, in particular here. Yeah, this is the one. And by the way, if you don't know the opcode of this instruction, you can go to options, general, and say, okay, I want to see 4 bytes of the opcode. And here, because it's a 32-bit application, so we can use 4 bytes for opcodes. And this is the opcode for jump +2. By the way, why we have here 0 and here +2? Because this EB operation code, this EB instruction, which is simple jump, it going to jump by default to +2 bytes, because the instruction itself is 2 bytes. So if it jumps, if it uses 0 and jumps to with a 0 offset, so it will jump to itself, and again it's going to be infinitely. But it's not very useful, except the our case when we want to attach the debugger, and that's why by default it adds +2. But the parameter, the argument for this jump is 0. If we again go to Google, jump rel 8, yeah, let's take any link. Hopefully it will provide enough. So in this case we use a relative jump and 8-bit offset. This is the EB type of jump. Then we need to provide the argument, and the argument in this case is 8-bit, and it is signed, so we can address any space from minus 128 bytes to plus 127 bytes. And why it differs? Because we use, as you know, from the course, university course of computer arithmetics, that there is a special code. I don't know the exact translation to English, like something like added code or complementary code, I believe, that is not just direct inverse of the positive value, because in such case, if we are going to directly inverse, this would mean that we have 2 zeros, right? And this is not best idea. And in this regard, we need to jump to -2, right? -2, because it will be by default added +2, and at the end we will have offset equal to 0, so we will jump to itself. And then there will be my second question, third question, apologize. What would be the opcode for this instruction? Again, EB stands for jump with 8-bit offset, which is a signed value, can be positive and negative. And just going back to our, so currently we have EB00, and that's why the answer EB00 doesn't work, because it will the implementation of jump instruction will add by default +2 bytes the size of this operation code. So we can, the first answer is incorrect. And then we have a choice between EBFF and EBFE. And again, if we are familiar with complementary code that should be studied at the Bachelor of Computer Engineering, at the Bachelor Program of Computer Engineering, then we would know that what is complementary code. So we need to inverse the value and sum and add 1. And if we inverse, we'll get the negative value, right? It will be F for FD. If we inverse +2, it will be FD. And then we need to do +1, because we don't want to have 2 zeros. And this means we have FD +1 will be FE. So the correct answer is EBFE. This is opcode for infinite loop. And the majority of you correctly answered this question. Okay, next step is just change it. So we're going to use like F2. So FE, and then I again press F2 or click apply changes. And now you can see that it's going to jump to DFF00. And now I can get back to my write function and release it. So the modified MBR will be executed. By the way, we are out of time. The recording will be available on YouTube later. So if you have another meeting, just drop and you can watch the ending of this presentation, of this webinar later. Then just release and see. Let's look at our file monitor here. So it is essential to verify if our MBR here has been successfully written, in particular 512 bytes to the offset 0. This is the beginning of our disk, bootable disk. And yeah, then we need just to reboot. But the thing is, in order to be able to use debugger, built-in VirtualBox debugger, we need to start this virtual machine with a special option. So I'm going to just shut down this. And this is just the command line that I'm going to use that would enable the dialog for debugging. So VirtualBox, the debugging capability of VirtualBox machines, they are disabled by default. And that's why we need to start it with debug capability enabled. So we don't need it anymore. Then you can see this is the menu that appeared when we enabled debugging. So I start command line, and here you can see the debugger. So currently our machine, as you can see, it's in infinite loop. It doesn't print the ransom note message. And what we need to do is type stop. So it's hard to see what I'm typing, but it will be reflected anyway in this console. So hopefully you're familiar with the CPU registers, and you will see that the current instruction pointer is 77C00. And if we take a look at this dumped MBR deassembler, this is a 7C00 is our jump, our patched version of jump. We can also see the code. So you can see jump -2, that's what we actually wanted to achieve. And then the rest of the code that coincides with the code here. So here we have exactly the same offset because it starts from 0 address, base address. And what I want to show you how it prints using this int 10h. So let's go back to our debugger. So what's interesting here, what is here? This is a pointer to string. Let's take a look what's here. C88. And I just printed the string value, ASCII string that is available by this address. So the string is, the pointer to the string is copied to SI register. And then, as you can see here, so this is where this SI register is initialized with the pointer to the string. And then, by the way, call +3 is just jumped to the next instruction. This is just, again, empty space for int3. Int3, it's a breakpoint. You can set int3 here. Then, increment, which means the string will be printed character by character. And finally we have this int 10 in mode OE, which is a teletype printing. So let's just use a step over Okay, we can't use step over, because what's going to happen when we step over, the instruction pointer is not going to change because it's infinite loop. So we have two options here. One option is to replace this jump instruction at the MBR at the disk. Another option just to change instruction pointer. The change instruction pointer is more easy and error-prone operation. That's why I'm going to use this. And to do that, by the way, I couldn't find the documentation on this VirtualBox debugger. Actually, I found, but it's very limited and outdated, and that's why if you want to see the help, just type the help, and there is a help comments, which provides you all possible operations that you can do with your, just make like this, how to step over, step in, how to print the values, how to dump the values, and yeah, how to resume, how to set breakpoint. The commands are, by the way, in the majority are the same as for Windows debugger. Pretty similar. And I'm going to use R, show or set registers active reg set, this operation. R EIP space equal sign and new value. So it's going to be 7C02, right? So I'm going to jump to the next instruction, 7C02. And then I can check the registers, and yeah, I can see that the EIP is now set to the next instruction. And then I can go debug step by step, and you can see it executes the instructions that were at the beginning of this MBR code. Well, and let's just for curiosity, let's go until you can use you can set breakpoint, but after you don't need it, you need to remove, and that's why sometimes it's just easier step over. And as you can see in the console of our VM, it's typing the ransom node. So it goes just one by one. And so if I, for example, want to print what SI has, we will see the rest of the strings that has not yet been printed in console. I think this part is clear. So we will resume, and the whole ransom node will be printed. But the interesting thing is, after this part, there is the second part, the second payload, the second feature of the destroyer. And in this case, we have another int interruption, 13, with the AH equal to 43H. I already, just to not to waste time switching between the windows, I already commented that this is this interruption with this parameter with this in this mode is extended write sectors to drive. So this is just writing some buffer to physical drive. And then we need to figure out before we are going to jump to this place, just what's going here. So first, it sets so-called disk access structure. So this is our this is anchor, right? That I mentioned. This is ransom node, and before that there is a space with configuration. This is the disk access packet (DAP) configuration. This provides information about, for example, the number, absolute block number. This is related to this value. For example, it's going to start writing the data to the absolute block number 1. What is absolute block number. When you address the physical disk, you have like two ways to do that. One way is to use the legacy notation CHS, cylinder head sector, which was used for this rotating physical drives, like old style physical drives, and new notation where you can just provide the ordering number of the sector. For example, LBA equal to 0. This is the first sector at the first cylinder at the first head. So the tuple that will be used to save the data is going to be like a 0, 0, 1. 0 cylinder, 0 head, and 1 is a value of the sector. Or yeah, suppose 0, because the addressing starts from 0. And yeah, if we have here 1, this means like will be used sector 1, 0, 0, 1. But LBA is more abstract and is used is more commonly used nowadays. Then we have a transfer buffer, which currently has 0, but it will be initialized 7C76. This is initialized here with the value 70C82 and 7C82. This is where this AAA anchor starts. So this is just a text message. It doesn't contain any code. So the buffer will be like this. And this buffer will be written to first to LBA1, because this is set by default. And then there is actually cycle, right? Jump here to 7C21 to the beginning of the loop. And at every iteration, it will add to the LBA 199 in decimal or 0C7, which means the destroyer is going to write this ransom note to every 199th LBA starting from 1. Why starting from 1? Because LBA 0 is actually MBR. So if it starts writing to LBA 0, it will just corrupt the code at the current MBR, which is currently running. That's why it starts from 0, and it sets, by the way, just for any case, if this block is corrupted, it sets 1 to this value. So that's shortly how it's going to work, and let's get back to the debugging procedure. And so now we are printing where we are. So I'm going to set up a breakpoint here, and this is a 7C21. 7C21. Then I can just resume my instruction pointer at 7C21, unassemble, and yeah, this is a breakpoint. We need to remove it in order to continue. And the debugger will recover this this instruction that is occupied by int3, which is used for debug. And then we have this int3 int13 with H843 with DAP configuration that I already mentioned, which was here set. And by the way, there is a ATH. This is a drive index. ATH stands for the first drive, which is typically C drive, system drive. And then, by the way, it's also iterated, if I'm not mistaken. So yeah, it's initialized to 0 and then incremented. Here, the drive index. So it means that all disks on the server will be corrupted. They will be written with this data. And then just let's go until the first write operation to our disk. By the way, we need to clean the breakpoint. Yeah, and then we can continue executing our program. Move AH, move AL, DL, where the transfer buffer is initiated. 88, it's drive index, as I mentioned, C drive. This is a pointer to DAP, data disk access packet. And yeah, let's see where we are currently. Just not to get lost. Yeah, this is, and yeah, the next will be 3F is execution of this interrupt. Yeah, it's been already executed. We can, by the way, see ensemble code, and yeah, and EIP currently is 7C41, which is here. Okay, we are done. So the ransom node is written to LBA1. How can we check that? And here we can use just go to VDI, VirtualBox VDI. I'm going to show you in a second. So hope you can see my file explorer. Go to snapshots, and so yeah, this is the latest modified VDI, and this is been actively being written by this application, by this MBR, and we can use hex edit and search for the anchor for them, right? Hopefully it will work. Or we can just, yeah, here is the hex value of this first hex byte of the strings I already entered here. Okay, let's look for. It searched for all occurrences. So this is by the way the code, the original code. You can see this is a EB00. This is the original code stored on hard disk. We are not pretty much interested in that. And there is one here. This one is more interesting because it has another base offset. The addressing system is not so straightforward as on a real physical disk, because it's virtual disk created by VirtualBox, and they have it has its own peculiarities. But what we can see here, that it was a replacement of some data in the middle of some other data. So we don't see any code. This is you can see code of some other application, and just in the middle of it, we can see this message, and we can see another message. Yeah, this is the original malware code. So if we just resume the application, we will see that more and more occurrences will appear. So let's get back to our debugging. Let's see if we have any. Yeah, I think we can just resume. And yeah, by the way, the whole ransom node is here in the console. And yeah, I think we don't need the debugger anymore. So we can just say bye and just get back. And yeah, I think we can close also virtual machine. No, we're going not to restore, and then go back to our hex workshop. It was, as you can see, the VDI has been updated. And let's search again for the occurrences of the string. And now you can see much bigger amount of the occurrences of this message. And if you compare the address, they will appear like after every 199 LB, and each LB represents one sector, and one sector is 512 bytes. You can just take in the address and calculating the difference. You will find out that this will be 199 multiplied by 512, which is bytes, which is the size of the sector. Which means it writes this ransom node at every 199th sector on the hard disk. And of course, this is not repairable. If even though you can, for example, restore your MBR using the disk, like rescue disk, Windows rescue disk, it will be not possible to recover your disk because they have this ransom node that overwritten the data on disk and prevents working the servers or computers. Okay, that's all what I wanted to tell you about MBR Writer, and I have a couple more slides about our project at the end of this presentation, and then I will open the Q&A session. So a few words about PROMIS project. So PROMIS project is designed to introduce modern courses, modern cybersecurity courses, and these courses include for spring 2022, advanced digital forensics, malware analysis, machine learning security, data-driven security, quality assurance of security-aware applications, and introduction to security in the software development lifecycle. So in particular, I'm responsible for malware analysis, and so I showed you briefly, yeah, I hope I hoped so, but it took a little bit more than I expected. How to analyze malicious programs, what techniques can be applied, like static analysis, dynamic analysis, debugging, and so on. And so the next slide will be, and this is the courses for autumn semester 2022. We have 4 more: development security applications, DevSecOps, security inventory for software development, applied cryptography, and security for critical infrastructure. And the last one, again, this is a course I'm responsible for, and this course is currently in development. So feel free to visit our page at promisedu.se, and if you have any questions, you can write our education manager, Anna Eriksson. And now, yeah, feel free to ask a question. Probably we don't have much time for questions, but if you have any, you can type in the chat or just turn online